gas optimization for efficient Ethereum smart contracts. This provides a comprehensive guide to optimizing gas usage in Ethereum smart contracts. It covers various techniques to reduce the cost of executing transactions and deploying contracts, making decentralized applications dApps more efficient and cost effective too. Understanding gas cost. Gas costs are determined by the complexity of the transaction or smart contract, including the number of operations and storage requirements. The analogy today we are going to use compares gas cost to the amount of fuel needed for a car trip, which depends on multiple factors like distance, speed, terrain, right? Weight of the car, luggage in the car, lot of factors matter. So what we are going to talk about is the efficient use of storage. Storage operations are expensive in terms of gas. We should optimize storage by minimizing the use of storage variables and using more efficient data structures. This analogy likens efficient use of storage to packing light for a trip to reduce fuel consumption. The less you carry, the less fuel you need, right? We've all gone on trips. You would have seen if you carry less luggage, you would require less fuel and you can save more fuel. So, similarly, that's how this works in blockchain. We're going to take code examples of inefficient storage versus optimized storage, and I'm going to tell you what the difference is between the two of them. Okay, so let's take the code examples. So in the first scenario, right, we are using dynamic array data. Okay, so this stores elements sequentially, accesses elements by index, right? So this is essentially what an array is. Whereas on the other hand, for the second code, we have mapping. So mapping stores key value pairs and elements are accessed using a key. This is suitable for scenarios where data is accessed randomly and needs to be associated with unique keys. The most important thing, efficiency and gas costs, right? So when you have a dynamic array, inserting or removing elements at arbitrary positions, what we are doing in this code here, right, can be quite expensive gas fees wise, as it may require shifting multiple elements. Whereas when you have mapping, you don't need to shift elements here, so the gas fees required is quite less. Hence, this is more optimized. Okay, then let's talk about the use cases. Dynamic array is used in case of simple list where elements are sequential. Mapping is used for scenarios like user balances, configurations, or lookups where keys are not sequential. Now let's talk about the gas cost considerations on both of them. Inserting or removing elements can have very high gas costs due to the need of shift elements, whereas mapping, retrieving a value by key, has a very low gas cost, no cost associated with maintaining order or shifting elements. Next is minimizing contract size. Deploying large contracts costs more gas. We should minimize contract size by modularizing the code and using libraries. This analogy compares minimizing contract size to packing only essentials for a trip to avoid extra baggage fees. You're going on a flight trip, right? You have a weight limit, 15 kg baggage limit. If you're carrying 20 kg, you need to pay more for extra baggage. So similarly, this is how minimizing contract size works, right? You only have the essential part of the code. Large contract. So a large contract is a monolithic contract with all functionality included, resulting in a larger contract size and very high deployment costs. Whereas what we are trying to achieve is a modular contract that utilizes libraries and modular code organization. It results in smaller contract size and much lower deployment costs. Okay, so let's look at the sample code we have here. What we have tried to achieve here is make a modular contract. Okay, so first what we have done is the library definition. We have used the library math library. We have defined math library. So what are libraries in Solidity? You have done it in other languages, right? So in Solidity, libraries are collections of reusable code that can be called by other contracts. They help in modularizing and reusing code. Okay, so next is your add function. Next is your function add UN256A, UN256B, internal pure returns UN256. Right, so this is basically a function named add that takes two UN256 arguments A and B and returns their sum. And you know what internal pure, right? So internal specifies that the function can be only called within the contract or library it is defined in, whereas pure indicates that this function does not read or modify the state of the blockchain. Next, we're just defining the contract. So the contract is called minimal contract, and we are using math library for UN56. This is basically the directive statement. It attaches the functions of math library to UN256 data type. In any UN256 variable can directly call the functions defined in math library. Okay. So your function is function add numbers UN256A, UN256B. Public pure returns UN256. So a function named add numbers that takes two UN256 arguments A and B and returns their sum. Again, this is public and pure, like what I just discussed with you right now, and return A dot add B. So this function calls the add function which is already present in the math library. We have not created a new function. This is already present. So it uses this function add on UN256 variable A with B as the argument, and it finally returns the result. Okay, so this is how we have designed a modularized contract. So next, you know what loops and functions are, right? Other programming languages, you have always used loops. And you must have always kept this in mind whenever you write code in any language, you should try to avoid the number of iterations in loop as much as possible. Same applies for Solidity, right? It's like essentially programming at the end. So loops and functions will obviously be gas intensive. So we optimize our code by minimizing loop iterations and avoiding unnecessary computations. This analogy, when we are using, it compares optimizing loops and functions to planning the shortest route for a trip to save fuel. Okay, so this is our code with the inefficient loop, right? So a loop that iterates over an array without caching the array length. Keep that in mind, this is not caching the array length, resulting in higher gas costs, right? Whereas in the second code, we have an optimized loop, a loop that caches the array length, reducing the number of operations and gas costs. So what's the difference between the two, right? So what's the difference between the two, right? So in the first one, we have an inefficient loop. In the first contract, the data.length property is accessed during each iteration of the loop. This results in an unnecessary gas cost for each iteration because reading the length of an array in Solidity is a storage read operation which is relatively quite expensive. In the second contract, the length of the data array is cached in a local variable length before the loop starts itself. This avoids repeated access to data.length during each iteration, reducing the number of storage reads. This approach is much more gas efficient, especially for large arrays. And obviously, the inefficient loop will cost more gas. Optimized loop will have much less gas fees. So in the first one, every time data.length is accessed, it incurs a storage read cost, right? Whereas in the optimized loop, by storing data.length in a local variable, which is cached essentially, before entering the loop, the contract performs the storage read only once. If you're doing something 100 times, if you're buying something 100 times, it'll cost you 100 rupees. Whereas if you're doing something only once, it'll cost you 1 rupee, right? So the first code is essentially you need to write something, you need a pen, right? So every time you need to write, you're buying 100 pens and you're always throwing them. You're buying a pen, using it, throwing it away. Buying a pen, using it, throwing it. You're doing this 100 times. In the optimized loop, you're using a pen, you're writing whatever you need to write, then you're closing the lid of the pen and keeping it with you. You have this one pen, and with this one pen, you're going to write 100 times. So this is much more gas efficient. Okay, now we have to learn how to use call data and memory efficiently. Right, so we use call data for function parameters that are read-only and memory for temporary variables to reduce gas cost. This analogy compares using call data and memory efficiently to organizing your luggage to access items quickly without unpacking everything. You have 5 bags, you want to look for t-shirts. You know that t-shirts are in bag 3. So instead of opening 1, 2, 4, 5, and then finally opening 3, if you directly open 3, it will save you much more money, right? It will save you much more of your resources. This is how this works too. So call data and memory. We use call data for read-only function parameters to save gas. We use memory for temporary variables to reduce gas costs. So let's look at the code over here. Right, we'll compare the code. So first of all, both contracts define a function that takes an array of UN256 values and returns the sum of the elements in the array. When we use call data is used for the data parameter, whereas when we use memory, memory is used for the data parameter, right? In the second code, memory is used, first code, call data is used. So in the first one, call data is non-modifiable. It is a read-only location where function arguments are stored. It is cheaper than memory because it avoids copying the data and is directly read from the transaction call data. Whereas on the second hand, memory is a temporary place where data is stored during function execution. It is modifiable and the data is copied to memory, which always incurs a cost. So when we consider the gas cost shortcut. When we consider the gas cost implications of both of them, right? Call data is much more gas efficient for read-only parameters because no additional memory allocation or copying is required. So lower gas cost for function execution. Whereas memory is less gas efficient compared to call data for read-only parameters due to the need for memory allocation and copying of data. It has higher gas cost compared to call data. Right? But there's also a pro and con. Call data, it is non-modifiable, whereas memory is always modifiable. You have to keep the merits and perks of both in mind while doing this, right? So the code is very easy, it's just a for loop. I'm pretty sure you'll get it. So I hope you got this. Next, what we are going to try and do is reduce external calls. External calls are gas intensive and can lead to re-entrancy vulnerabilities. We have discussed these in previous videos in great detail. You can always refer back to them if you have any confusion. So we try to reduce the number of external calls and use internal functions wherever possible. This analogy compares reducing external calls to minimizing stops on a road to save time and fuel. So an external call is gas intensive, whereas an internal function is much more gas efficient. Right? An external call has potential re-entrancy vulnerabilities, whereas an internal function has no re-entrancy risks. External call has slower execution, whereas an internal function has much faster execution. Let's go through this code. This is essentially external call optimization, right? So you have state variables, a mapping that balances is your state variable, a mapping that associates each user's address with their balance, keeps track of the funds deposited by each user. Then you have your deposit function, right? It's publicly visible. So the function can be called by any external address, right? And the function is marked payable to allow it to receive ether. And the logic it follows is it adds the amount of ether sent with the transaction message.value to the balance of the sender message.sender. Basic transfer of funds, right? Of ether essentially. Then you have your withdraw function. Your withdraw function is also public, can be called by any external address, right? The parameter used here is amount of ether to withdraw. Okay, so the logic. First, this has a require statement. So this always ensures that the user has enough balance to withdraw the specified amount. Otherwise, it returns insufficient balance. So then we update balance before external call. So this reduces the user's balance by the specified amount before making the external call. This is the best practice to avoid re-entrancy attacks. So this is the special step we are doing here. We are updating the balance before the external call. Next, we are using call to send ether to the user. The call method is preferred over transfer or send as it forwards all available gas and handles more complex scenarios. Right? And it checks if the call was successful and it reverts the transaction if it was not. This helps what we have done here is we have minimized external calls and this has helped in protecting us against re-entrancy attacks. Now we'll just go through a comprehensive code example utilizing all of these techniques that we have used, right? Efficient storage, call data, memory, reducing external calls. We'll use everything all in one code. So this would just be a summary of everything, right? Okay, so let's break down the code for you. First, we are importing from OpenZeppelin the contract ownable.sol, right? This includes ownership related functions and modifiers. Next, we are importing safemath.sol. This provides safe mathematical operations, preventing overflow and underflow errors. Next is inheritance. The contract inherits from ownable, making it possible to restrict certain functions to only the owner of the contract. Then you have your state variables, balances, which is a mapping, and data, which is an array that stores uint56 values. So here you have two events, the deposit event and the withdrawal event. So you have a function. So please keep in mind that you have two different scenarios. One, you have events also and functions. They both have similar names. You have a deposit function and a deposit event, but they're different. Okay, please keep that in mind. Deposit is capital D deposit event, right? And the function is small d deposit. Okay, so there's a difference, right? So the function, it has public visibility and it is marked as payable. So it updates the user's balance using safemat.add to prevent overflow. And it emits a deposit event with the user's address and the amount deposited. So please be careful here again. At the end, the deposit function emits a deposit event, capital D event, right? with the user's address and the amount deposited. Okay, so right, this is your deposit function, and similarly, you have a withdraw function. Now, again, this is also public, right? And it has a parameter that it takes, which is the amount of ether to withdraw. So this also has a requirement. It ensures that the user has sufficient balance. And as we did in the previous slide itself, we update the user's balance before making the external call. This was due to checks, effects, interactions pattern to prevent any reentrancy attacks. So it uses call with a gas limit of 20,000 to send ether. This is to prevent out of gas errors and ensure a safe transfer. It reverts the transaction if the transfer fails. And again, the withdraw function at the end of everything emits a withdrawal event, capital W withdrawal event, with the user's address and the amount withdrawn. Right? So again, please be very careful. I am repeating this multiple times. The withdraw function at the end emits a withdrawal event. And then you have your add data function. This adds a value to the data array, public visibility. Anyone can call this function. Then you have a sum optimized data function, right? So it sums the elements of the data array. It's public view. Anyone can call this function, and it does not modify the state of the contract. And optimization takes place here because it caches the length of the array to reduce gas usage by avoiding repeated length hookups. This is what we have done, right? We have cached the length of the array before itself to avoid repetitive iterations and loops and increasing the gas cost. So we are minimizing the gas cost here. Then you just have your process data function, right? Again, sums the elements of an input array. Anyone can call this function because it's public and pure, and it doesn't modify or read the state, right? Because it's pure. And the data location here is it uses call data for the input data parameter, which is much more gas efficient for read-only parameters, right? You use call data when you have read-only parameters. This code that we have generated here has been used for security enhancements and gas optimization too, right? So this is essentially it. The use of comprehensive example, right? This basically what it showed us using gas optimization techniques, right? So analogy wise, it compares this to building an efficient smart contract to planning a fuel efficient road trip with minimal stops and well organized luggage. So we'll finally summarize everything. We'll recap all key points. We optimize storage by minimizing the use of storage variables and using efficient data structures. Next, we minimize the contract size by modularizing the code and using libraries. After that, we optimize loops and functions by minimizing iterations and avoiding unnecessary computations. After that, we proceed to use call data for read-only function parameters and memory for temporary variables. So then we also try to reduce the external calls to save gas and prevent vulnerabilities. After this, I have a simple interactive exercise or quiz for you. What you can try to do is implement a function that optimizes storage by using a mapping instead of an array. Refactor the large contract into a smaller one. Use modular contracts using libraries, right? And we have to optimize the loop to minimize gas usage. Use call data for function parameters in a given function. And we can reduce the number of external calls in a provided smart contract. So this is the exercise or quiz for you. I think with this concludes our segment of the video today. Thank you very much for watching. Bye.